In the deepest vault beneath the Japanese Alps, 3,000 feet underground, sits a tank containing 50,000 tons of the purest water on Earth. Scientists have been watching this water for over 2 decades, waiting for something that might never happen. They're waiting for a single proton to die. And if they're right about what they might see, everything you think you know about forever is about to change. We assume atoms are eternal. The proton in your body, forged in the first minutes after the Big Bang, should outlast every star in the universe. But what if we're wrong? What if the very particles that make you possible are slowly decaying away, grain by grain, until nothing remains but empty space and the faintest whisper of energy? Today, we journey into the most patient experiment ever conceived. We'll explore why the death of a single particle could rewrite the laws of physics. We'll witness the cosmic countdown that began 13.8 billion years ago and discover why the universe might be designed to erase itself completely. This isn't just about particles. This is about the ultimate fate of everything that has ever existed or ever will exist. The story of how the universe dies starts with the smallest building block of matter, and it's more beautiful and terrifying than you could imagine. Deep inside every atom in your body lies a mystery that has haunted physicists for half a century. Your protons should be immortal. According to everything we thought we knew about particle physics, these fundamental building blocks of matter cannot decay. They have no smaller components to break apart into. They carry electric charge that must be conserved. They seem to violate every mechanism we know for particle destruction. Yet the most successful theories in physics predict they must die. Think about this for a moment. Every proton in your body has existed since the universe was 3 minutes old. They survived the formation of the first atoms, the birth and death of countless generations of stars, the creation of our solar system, and the entire history of life on Earth. These particles have been with you since before you were born and will outlast every civilization humanity might ever build. But according to grand unified theories, even these ancient survivors are living on borrowed time. The prediction emerges from our attempts to understand why the universe looks the way it does. In the beginning, the Big Bang should have created equal amounts of matter and antimatter. When matter meets antimatter, they annihilate completely, leaving nothing but pure energy. Our universe should be empty, filled only with photons racing through an endless void. Instead, we exist. Something broke the symmetry between matter and antimatter, allowing a tiny excess of matter to survive the cosmic annihilation. Grand unified theories suggest this asymmetry requires processes that violate one of the most sacred laws of physics: baryon-number conservation. Baryons include protons and neutrons, the particles that make up atomic nuclei. Baryon-number conservation means these particles cannot simply disappear. You cannot destroy a proton without creating another baryon somewhere else. This law seems absolute, written into the fundamental structure of reality itself. But if this law can be violated even slightly, it opens a door to something profound and disturbing. Protons could decay into lighter particles, converting matter into energy, according to Einstein's famous equation. The process would be extraordinarily rare, so unlikely that you could watch a single proton for billions of years without seeing it happen. Yet, in a universe containing countless protons, even the most improbable events become inevitable given enough time. The mathematics are staggering. Current theories predict that a proton's lifetime might be around 10 circumflex 34 years. To put this in perspective, the universe is currently 13.8 billion years old, which is about 10 circumflex 10 years. The predicted proton lifetime is 24 orders of magnitude longer than the current age of the cosmos. Imagine if a single second represented the entire history of the universe from the Big Bang until now. On that scale, the proton lifetime would be longer than the age of the universe, by the same factor that the age of the universe exceeds 1 second. It's a span of time so vast that human language lacks adequate words to describe it. But here's what makes this prediction testable. Despite the impossible timescales involved, you don't have to wait 10 circumflex 34 years to see proton decay. You just need to watch enough protons. If you observe 10 circumflex 34 protons for 1 year, statistical probability says you should see roughly 1 decay during that time. The challenge becomes assembling enough matter to contain that many protons while eliminating every possible source of background noise that might mimic the signal you're looking for. This is where the story becomes almost absurdly ambitious. Scientists have built detectors containing thousands of tons of the purest materials on Earth, buried them miles underground to shield them from cosmic rays, and surrounded them with layers of sophisticated instruments designed to catch the faintest traces of proton death. The Super-Kamiokande detector in Japan contains 50,000 tons of ultrapure water surrounded by over 11,000 photomultiplier tubes that can detect individual photons of light. When a proton decays, it should produce a characteristic flash of light as the decay products interact with surrounding water molecules. The pattern of this flash would tell physicists exactly what happened to the dying proton. But after more than 20 years of continuous observation, Super-Kamiokande has detected nothing. The absence of proton decay signals has pushed the predicted proton lifetime beyond 10 circumflex 34 years, creating a tension between theory and experiment that grows more uncomfortable each year. Either grand unified theories are wrong about the mechanisms that created matter-antimatter asymmetry, or protons live even longer than our most conservative estimates suggested. Some physicists argue that proton decay might be so rare that we need detectors containing millions of tons of material watched for decades before we see our first event. Others suggest that the decay modes we're looking for might be incorrect, and protons might die through completely different pathways that produce signals we haven't learned to recognize yet. The implications extend far beyond particle physics. If protons are truly stable, then atoms could exist forever, and the universe might approach a state of maximum entropy where nothing changes but nothing truly dies. But if protons decay, even at the incredibly slow rates current theories suggest, then the story of cosmic evolution has a very different ending. Consider what proton decay means for the distant future. Long after the last star is burned out and the last black hole has evaporated, protons would continue their slow dissolution. The atoms in dead planets would gradually disintegrate, releasing their energy as photons and lightweight particles that spread throughout the expanding universe. Eventually, every atom that ever formed would return to the quantum vacuum from which it emerged. The elements forged in stellar cores, the carbon and oxygen and nitrogen that made life possible, would all dissolve back into pure energy. Even the iron in your blood and the calcium in your bones would eventually succumb to the cosmic tendency toward dissolution. This process would take so long that it defies human comprehension. The protons in your body would likely survive unchanged for 1,000 trillion times longer than the universe has currently existed. By the time the first protons began to decay in significant numbers, the expansion of space would have carried the remnants of our galaxy so far from other galaxies that future observers, if they existed, would see nothing but darkness in every direction. Yet the mathematics of probability ensure that even these ancient particles must eventually yield to the quantum fluctuations that govern all matter at the smallest scales. The search for proton decay represents one of the most patient scientific endeavors ever undertaken. Researchers dedicate their entire careers to experiments that might never see the phenomenon they're designed to detect. They improve detector sensitivity year after year, pushing the limits of what's technically possible while knowing that success might require waiting longer than human civilization has existed. But the absence of detected proton decay carries its own profound implications. Every year that passes without a confirmed detection tells us something important about the stability of matter and the ultimate fate of the universe. The longer protons survive, the longer the universe retains the possibility of complexity, structure, and perhaps even consciousness existing in some form. Current experiments are approaching sensitivity levels that could detect proton lifetimes up to 10 circumflex 35 years. Future detectors might push this limit even higher, watching vast quantities of matter with unprecedented precision for decades at a time. The technology required for these experiments pushes the boundaries of human engineering. The water in Super-Kamiokande must be purer than anything found in nature, with contaminant levels measured in parts per billion. The photomultiplier tubes that line the detector walls can register single photons of light arriving from any direction. The entire facility operates at temperatures just above freezing to minimize thermal noise that could mask the signals physicists are seeking. Underground laboratories around the world house similar experiments, each designed to catch different aspects of proton decay or to confirm results obtained by other detectors. The international collaboration required for these projects spans decades and involves thousands of scientists working toward a common goal that none of them might live to see achieved. But the absence of proton decay signals doesn't mean the experiments are failures. Every negative result constrains the possible theories that describe how the universe works at its most fundamental level. Each year of data collection rules out entire classes of grand unified theories while pointing toward new possibilities that physicists hadn't previously considered. The story of proton decay touches the deepest questions about the nature of time, matter, and existence itself. Are there truly eternal particles in the universe? Or does everything eventually return to the quantum foam from which it emerged? Is the complexity we observe around us a temporary arrangement that will ultimately dissolve? Or could the universe maintain structure indefinitely? These questions become more urgent as our understanding of dark energy suggests that the expansion of space is accelerating. In a universe that continues to expand at an ever-increasing rate, the dissolution of matter through proton decay might represent the final chapter in cosmic evolution, the last process that could release energy into a cold and empty cosmos. The detection of even a single proton decay would revolutionize physics and cosmology simultaneously. It would confirm that the universe contains no truly permanent structures, that even the most stable particles must eventually yield to the relentless mathematics of quantum mechanics. It would also validate grand unified theories that attempt to explain why matter defeated antimatter in the cosmic struggle that allowed our existence. But the continued absence of proton decay signals preserves the possibility that the universe might be stranger and more resilient than our current theories suggest. The mathematics of forever become even stranger when you consider what lies beyond proton decay. Even if every proton in the universe eventually dissolves, the story doesn't end there. We enter a realm where time itself becomes the enemy of existence, where the very concepts of permanence and stability lose all meaning. Welcome to the age of quantum tunneling, where even the most impossible events become inevitable, given enough time. In the far future, long after proton decay has reduced all matter to its simplest components, the universe will be populated primarily by electrons, neutrinos, and photons. These particles, as far as we know, are truly stable. They have no internal structure to decay, no conservation laws that might be violated to allow their destruction. But quantum mechanics has one final trick up its sleeve. Quantum tunneling allows particles to spontaneously appear on the other side of energy barriers that should be impossible to cross. It's the process that powers the sun, allowing protons to fuse despite lacking the energy to overcome electromagnetic repulsion through classical physics alone. In stellar cores, quantum tunneling happens constantly, enabling nuclear reactions that keep stars burning for billions of years. But tunneling can work in reverse too. In the unimaginably distant future, Quantum tunneling could allow even stable particles to spontaneously transform into configurations with lower energy states. An electron might tunnel into a state where it no longer exists as a particle, converting its entire rest mass into energy, according to Einstein's equation. The timescales involved make proton decay seem rapid by comparison. While protons might live for 10 circumflex 34 years, quantum tunneling effects for stable particles might not become significant for 10 circumflex 150 years or longer. These numbers transcend human intuition so completely that they exist purely in the realm of mathematical abstraction. To visualize such timescales, imagine writing the number 1 followed by 150 zeros. If each zero were the size of an atom, the resulting number would stretch across a distance millions of times larger than the observable universe. Yet this represents just the beginning of the timeline over which quantum tunneling might finally eliminate the last remnants of matter. During this era, the universe will have expanded so dramatically that individual particles will be separated by distances larger than galaxies today. The cosmic microwave background radiation will have been stretched to wavelengths measured in light years. Space itself will be colder than anything we can currently imagine, approaching absolute zero with mathematical precision. In this frozen cosmos, quantum tunneling becomes the only source of activity. Occasionally, perhaps once every 10 circumflex 100 years, a particle will spontaneously tunnel into a lower energy state, releasing a tiny flash of energy that propagates through the void at light speed. These rare events will be the only things happening anywhere in the universe. But even quantum tunneling has its limits. Eventually, after timescales that dwarf the age of proton decay by factors too large to express in ordinary notation, all particles will have tunneled into their lowest possible energy states. The universe will reach a condition of maximum entropy, where no further energy can be extracted from any process. This is the heat death of the universe, the final equilibrium state where nothing can change because there are no energy gradients left to drive any process. Temperature will be uniform throughout space. No work can be performed. No information can be processed. The universe will exist in a state of perfect, eternal stillness. Yet even this might not represent the absolute end of cosmic evolution. Recent developments in quantum mechanics suggest that the vacuum of space itself might be unstable over truly astronomical timescales. The Higgs field, which gives particles their mass, might exist in a false vacuum state that could spontaneously decay into a lower energy configuration. If this happened, it would rewrite the laws of physics throughout the affected region, potentially annihilating everything in its path. A vacuum decay event would propagate outward at the speed of light, creating an expanding sphere of altered physical laws. Nothing could escape because no information travels faster than light. We would have no warning of its approach until the moment it arrived to restructure the fundamental nature of reality itself. Inside a vacuum decay bubble, particles might have different masses or might not exist at all. The forces that hold atoms together could be stronger or weaker, making chemistry impossible. The fine structure constant that determines how light interacts with matter could take on new values, rendering the universe transparent or opaque in ways we cannot predict. From the perspective of observers inside the decay bubble, if any could exist under the new physical laws, the transition would be instantaneous. One moment they would inhabit our familiar universe with its quarks and electrons and electromagnetic forces. The next moment would bring entirely different physics, possibly incapable of supporting any form of complexity or consciousness. The probability of vacuum decay is extraordinarily small on human timescales. Current calculations suggest it might not occur for periods vastly longer than proton decay timescales. But quantum mechanics guarantees that any process with non-zero probability will eventually happen given infinite time. This raises a profound question about the nature of eternity itself. If the universe truly exists forever, then every possible quantum event, no matter how improbable, must eventually occur. Vacuum decay becomes not just possible, but inevitable. The heat-death scenario transforms from a permanent end state into a temporary equilibrium that will eventually be disrupted by quantum fluctuations. In the infinite future, the universe might cycle through countless phases of expansion, decay, and renewal. New physics might emerge from vacuum decay events, creating conditions where entirely different forms of matter and energy can exist. What we consider the fundamental laws of nature might represent just one temporary configuration in an endless sequence of physical realities. Some physicists speculate that vacuum decay could even create new universes with different dimensional structures. A decay event might spawn a region of space with 4 spatial dimensions instead of 3, or where time flows in multiple directions simultaneously. These pocket universes would be forever inaccessible to us, separated by boundaries where the very meaning of space and time undergoes radical transformation. The implications extend beyond physics into philosophy and theology. If vacuum decay can create infinitely many different versions of physical law, then every possible universe might eventually exist somewhere in the vast landscape of quantum possibilities. This multiverse would contain realities where life never formed, where consciousness never emerged, and where the questions we ask about existence have no meaning. But it would also contain universes where life found ways to survive and thrive under conditions we cannot imagine. Perhaps consciousness itself proves more resilient than matter, finding ways to encode itself in quantum fields or space-time geometry that persist through vacuum decay transitions. The search for proton decay thus represents more than an investigation into particle physics. It's an attempt to understand whether the universe contains any truly permanent features or whether everything we observe exists in a temporary equilibrium that will eventually dissolve into something entirely different. Current experiments push the boundaries of what's technically possible in the search for these ultimate answers. The next generation of detectors will contain hundreds of thousands of tons of target material, watched by instruments sensitive enough to detect individual particle interactions with unprecedented precision. Deep underground facilities are being excavated to house these massive experiments. The Hyper-Kamiokande detector, currently under construction in Japan, will contain 260,000 tons of ultrapure water surrounded by 40,000 photomultiplier tubes. Its sensitivity will exceed current detectors by an order of magnitude, potentially detecting proton lifetimes up to 10 circumflex 35 years. Similar projects are planned in the United States, Europe, and China. The Deep Underground Neutrino Experiment will use 70,000 tons of liquid argon to search for proton decay while simultaneously studying neutrino oscillations. The European Spallation Source Neutrino Superbeam will combine proton decay searches with precision measurements of matter-antimatter asymmetry. These experiments represent humanity's most ambitious attempt to understand the ultimate fate of matter itself. They require international collaboration on unprecedented scales, with thousands of scientists dedicating their careers to questions that might not be answered for decades. The technology needed for these detectors pushes every engineering discipline to its limits. The photomultiplier tubes must operate reliably for years without maintenance while detecting single photons against backgrounds of thermal and radioactive noise. The purification systems must remove trace contaminants to levels that approach fundamental quantum limits. Underground laboratories must be excavated to depths that provide shielding equivalent to thousands of feet of rock while maintaining clean room conditions throughout enormous volumes. The data acquisition systems must record and analyze petabytes of information while distinguishing genuine proton decay signals from countless background events that mimic the signatures physicists are seeking. But perhaps the most remarkable aspect of these experiments is their time horizon. The scientists designing them know they might never see the phenomena they're looking for. They're building instruments for future generations, creating legacies of human curiosity that will outlast any individual career or lifetime. The search for proton decay embodies humanity's deepest impulse to understand our place in the cosmic story. We want to know whether the atoms that make us possible will survive forever, or whether we exist during a brief moment of stability in a universe that tends inexorably toward dissolution. The answers we seek might be hiding in plain sight, written in the language of particles too small to see and timescales too vast to comprehend. But there's something even stranger waiting in the mathematics of forever, something that makes proton decay look like a gentle fade compared to the violent resurrection that quantum mechanics has in store. Imagine the universe after every proton has decayed, after quantum tunneling has eliminated every electron, after the last photon has been stretched by cosmic expansion until its wavelength spans light years. You might think this represents the end of the story, a universe finally at rest after 10 circumflex 100 years of slow dissolution. But quantum mechanics has other plans. In the deepest reaches of quantum field theory lies a prediction so bizarre that even physicists struggle to accept its implications. The quantum vacuum isn't empty. It seethes with virtual particles that pop into existence and annihilate each other in time frames so brief they exist below the threshold of measurement. These fluctuations happen everywhere, all the time, even in the apparent emptiness between galaxies. Most virtual particle pairs disappear immediately, their borrowed energy paid back to the vacuum before the universe notices the debt. But occasionally, in events so rare they defy human intuition, these fluctuations can become real. A virtual particle pair might spontaneously gain enough energy to become permanent, adding new matter to the universe from pure nothingness. The probability is infinitesimally small. You could watch a single cubic meter of empty space for periods longer than the current age of the universe and never witness such an event. But in an infinite cosmos with infinite time, even the most improbable events become mathematically certain. This means the heat death of the universe might not be permanent. After unimaginable eons of perfect stillness, quantum fluctuations will begin to generate new particles from the vacuum. A photon might appear here, an electron-positron pair there, each materialization adding tiny amounts of energy back into the cosmic void. At first, these events will be separated by timescales that make proton decay seem frequent. Perhaps one new particle every 10 circumflex 150 years across the entire observable universe. But as space continues to expand, the volume available for quantum fluctuations grows exponentially, increasing the probability that somewhere, something new is being born from nothing. Over periods so vast they transcend mathematical notation, these rare events will accumulate. Random quantum fluctuations will occasionally align in ways that create not just individual particles, but complex arrangements of matter and energy. Hydrogen atoms might spontaneously assemble from vacuum fluctuations, their protons and electrons materializing in precisely the right configurations to form stable matter. The process sounds impossible, but the mathematics are unforgiving. Given infinite time and infinite space, every possible arrangement of particles will eventually emerge from quantum fluctuations. Not just once, but infinitely often, the universe will spontaneously regenerate itself through pure chance, creating new epochs of complexity from the ashes of cosmic dissolution. These quantum resurrections will follow no pattern or plan. Most fluctuations will produce nothing more than isolated particles that drift through the void for eons before encountering anything else. But occasionally, random chance will create more elaborate structures. A cloud of hydrogen gas might materialize in some distant region of space, dense enough to begin gravitational collapse. Over billions of years, this randomly generated matter cloud will contract under its own gravity, heating up until nuclear fusion ignites in its core. A new star will be born, not from the remnants of previous stellar generations, but from pure vacuum fluctuations that happen to align in just the right way. This star will burn for millions of years, fusing hydrogen into helium and eventually synthesizing heavier elements in its core. When it exhausts its fuel, It might explode as a supernova, scattering these newly created elements throughout surrounding space. Or it might collapse into a black hole, warping space-time around itself and beginning the slow process of Hawking radiation that will eventually return its mass to the vacuum. But here's where the story becomes truly extraordinary. Quantum fluctuations don't just create simple structures like stars and planets. Given enough time and enough random attempts, they will eventually produce every possible arrangement of matter and energy that the laws of physics allow. Somewhere in the infinite future, quantum fluctuations will spontaneously generate the exact arrangement of atoms that makes up your body. Not similar to your body, but identical down to the last quark and electron. The same neural patterns that create your thoughts, the same memories encoded in the structure of your brain, the same conscious experience that is reading these words right now. This quantum twin will exist for a brief moment before thermal motion and radioactive decay begin to alter their structure. But during that moment, they will be you in every meaningful sense. They will have your memories, your personality, your fears and hopes and dreams. They will believe they have lived your entire life up to that point, never suspecting they materialized from random vacuum fluctuations just moments before. The mathematics guarantee this will happen not just once, but infinitely many times. Every possible variation of your life will eventually emerge from quantum fluctuations. Versions where you made different choices, where history unfolded along alternative paths, where the fundamental constants of physics took slightly different values. Some of these quantum resurrections will be brief, lasting only microseconds before dissolving back into the vacuum. Others might persist for billions of years, living entire lifetimes in universes that spontaneously generated the conditions necessary to support consciousness and complexity. The implications are staggering. Every person who has ever lived will be reborn countless times through quantum fluctuations. Every civilization that has ever existed will reassemble itself from random chance. Every possible civilization that could exist will eventually emerge from the vacuum, explore its potential, and fade back into nothingness. But these resurrections will be separated by timescales so vast that each one exists in complete isolation. By the time quantum fluctuations recreate Earth and humanity, the original versions will have been gone for periods longer than the current age of the universe by factors that require scientific notation to express. Each quantum resurrection will believe it is the original, the first, the only version of itself that has ever existed. They will have no memory of previous incarnations because those memories dissolved along with the matter that encoded them eons earlier. Every quantum twin will discover the universe anew, ask the same questions about existence and meaning, and eventually succumb to the same cosmic forces that claimed their predecessors. The cycle becomes infinite and eternal. Creation from nothing, evolution of complexity, inevitable dissolution, and rebirth through random chance. The universe transforms from a story with a beginning, middle, and end into an endless loop where every possible story plays out infinitely often. This quantum eternity raises profound questions about the nature of identity and consciousness. If exact copies of you will spontaneously emerge from vacuum fluctuations in the distant future, are they you or merely identical replicas? Does consciousness persist across these vast gaps in time? Or does each quantum resurrection represent a completely new being that happens to share your memories and personality? Some physicists argue that identity is purely informational. If the quantum arrangement of particles that creates your consciousness is perfectly reproduced, then the resulting being is you in every meaningful sense. The gap in time between your current existence and your quantum resurrection is no different from the gap between falling asleep and waking up. Others contend that consciousness requires continuity. Each quantum twin might be identical to you in every measurable way, but they lack the unbroken stream of experience that connects your present moment to your past. They are sophisticated copies, but copies nonetheless. The debate touches the deepest mysteries of consciousness and personal identity. What makes you, you? Is it the specific arrangement of atoms in your brain? Or something more fundamental that transcends physical structure? Do you persist through the constant turnover of cells in your body? Or are you already a different person than you were 7 years ago when every atom in your body was replaced? Quantum resurrection forces us to confront these questions on cosmic scales. If perfect copies of you will exist in the infinite future, created by random chance rather than biological reproduction, what does that mean for the significance of your current life? Are you living your only existence? Or are you one instance in an infinite series of identical beings? The mathematics of quantum fluctuations suggest an even stranger possibility. Not only will exact copies of you emerge from the vacuum, but improved versions will also spontaneously generate. Random chance will occasionally create beings with your memories and personality, but enhanced intelligence, perfect health, or capabilities you never possessed. These quantum upgrades will be incredibly rare, requiring fluctuations so improbable that they might occur only once across timescales that dwarf the age of proton decay. But infinity guarantees their eventual existence. Somewhere in the vast future, a version of you with perfect memory, unlimited creativity, and immunity to aging will materialize from pure vacuum fluctuations. They will inherit your identity, but transcend your limitations. They might solve problems that plagued your original existence, achieve goals you never reached, or experience forms of happiness and fulfillment beyond your current capacity. Yet they will still be you, carrying forward your essential consciousness into realms of possibility you cannot imagine. The implications extend beyond individual consciousness to encompass entire civilizations and species. Quantum fluctuations will eventually recreate not just human beings, but enhanced versions of humanity with capabilities that exceed our current potential. These quantum civilizations might develop technologies that allow them to survive longer, explore deeper, or understand more than their predecessors ever could. Some quantum resurrections might generate civilizations wise enough to recognize their origins in vacuum fluctuations. They might understand that they are temporary arrangements of matter and energy, destined to dissolve back into the quantum foam that created them. This knowledge could lead to profound philosophical and spiritual insights about the nature of existence and the meaning of consciousness in an infinite universe. Other quantum civilizations might develop technologies that allow them to persist longer than natural processes would normally permit. They might learn to harness the energy of vacuum fluctuations themselves, creating self-sustaining systems that resist dissolution. Or they might discover ways to encode their consciousness in forms that survive the transition back to pure energy. The search for proton decay thus represents more than an investigation into the ultimate fate of matter. It's a window into questions about the nature of time, identity, and existence that will remain relevant long after every proton in the universe has dissolved. Understanding how matter dies helps us understand what it means to live in a universe where death might not be permanent. Current experiments searching for proton decay are pushing the boundaries of human technology and patience in pursuit of answers that could reshape our understanding of forever itself. The detectors buried deep underground in laboratories around the world represent humanity's attempt to witness the first chapter of cosmic dissolution, the initial step in a story that leads ultimately to quantum resurrection and infinite renewal. But the absence of detected proton decay tells its own story about the resilience of matter and the patience of the universe. Every year that passes without a confirmed detection extends the predicted lifetime of protons, pushing the timeline of cosmic dissolution further into the future. The atoms that make up your body, forged in stellar cores billions of years ago, might survive for periods so vast that quantum fluctuations will recreate entire universes before the first protons begin to decay. This temporal resilience of matter creates a profound tension in our understanding of cosmic evolution. On one hand, the universe appears to be expanding and cooling toward a state of maximum entropy, where nothing can change. On the other hand, the incredible longevity of protons suggests that complex structures might persist far longer than early cosmological models predicted. The resolution of this tension depends on discoveries that might not come for decades or centuries. Future experiments will probe deeper into the quantum structure of matter, searching for the subtle processes that govern particle decay at the most fundamental level. They will map the landscape of possible vacuum states, determining whether our current reality represents a stable configuration or merely a temporary arrangement that will eventually transition to something entirely different. These investigations will require technologies that don't yet exist and collaborations between scientists who haven't yet been born. The questions raised by proton decay research transcend individual careers and lifetimes, becoming part of humanity's long-term project to understand our place in the cosmic story. Yet the search continues with patient dedication that mirrors the cosmic timescales being investigated. In underground laboratories around the world, detectors filled with ultra-pure water and liquid argon watch for the faintest flashes of light that might herald the death of a proton. Each day of observation adds to a dataset that will eventually span decades, creating the most comprehensive record of particle stability ever assembled. The scientists who dedicate their careers to these experiments understand that they might never see the phenomena they're searching for. They're building knowledge for future generations, contributing to a scientific legacy that will outlast any individual contribution. Their work embodies the same long-term perspective that governs cosmic evolution itself, patient observation in service of understanding that transcends immediate gratification. This patience becomes a form of cosmic meditation, an acknowledgement that the most profound questions about existence require timescales that exceed human lifespans. The search for proton decay teaches us to think beyond the immediate, to consider our place in stories that began billions of years before we were born and will continue billions of years after we're gone. In this context, the question of whether protons decay becomes a question about the nature of permanence itself. Are there truly eternal features in the universe? Or does everything eventually yield to the relentless creativity of quantum mechanics? The answer will shape our understanding of what it means to exist in a cosmos where nothing stays the same forever, yet everything might return again through the patient mathematics of infinite time. The mathematics of quantum resurrection reveal something even more unsettling about the nature of consciousness and time. In the vast reaches of the future, after every proton has dissolved and every black hole is evaporated, the vacuum will not simply generate random arrangements of particles. It will create perfect reproductions of every moment that has ever existed. Consider this carefully. Right now, as you read these words, your brain exists in a specific configuration. Every neuron, every synapse, every quantum state that creates your current thoughts is arranged in a precise pattern. This pattern represents not just your physical structure, but your entire conscious experience at this exact moment. In the infinite future, quantum fluctuations will spontaneously recreate this exact configuration. Not similar to your current brain state, but identical down to the last electron. When this happens, that quantum brain will experience this precise moment of consciousness again. It will think these same thoughts, feel these same emotions, and wonder about these same cosmic questions. But here's where the story becomes truly strange. The quantum vacuum doesn't just recreate isolated moments of consciousness, it generates entire sequences of connected experiences. Somewhere in the vast future, fluctuations will create your brain in the state it existed yesterday, then today, then tomorrow, linking these moments into continuous streams of awareness that span days, years, or even entire lifetimes. These quantum sequences won't follow the same timeline you're experiencing now. They might play out in reverse, with effects preceding causes and memories forming before the events they recall. Or they might skip randomly through different periods of your life, creating consciousness that jumps between childhood and old age without following linear time. The implications challenge everything we think we know about the relationship between memory and experience. If quantum fluctuations can create a brain with memories of events that never happened in that particular cosmic epoch, what defines authentic experience? Are memories valid only if they correspond to actual historical events, or do they carry meaning regardless of their origin? Some quantum resurrections will generate beings with false memories of civilizations that never existed in their timeline. They'll remember technologies that were never invented, relationships with people who were never born, and histories that unfolded along entirely different paths. Yet these memories will feel completely real because the neural structures that encode them are identical to those created by genuine experience. This creates infinite libraries of possible histories, each as valid from the perspective of the consciousness experiencing it as any actual historical record. The universe becomes not just a collection of matter and energy evolving through time, but a vast repository of every possible experience that conscious beings could ever have. The timescales involved in quantum resurrection make the predicted lifetime of protons seem brief by comparison. While protons might survive for 10 circumflex 34 years, the spontaneous generation of complex conscious beings from vacuum fluctuations might not occur for 10 circumflex 50 years or longer. These numbers exist so far beyond human comprehension that they lose all practical meaning, becoming pure mathematical abstractions that describe processes more patient than anything in our current experience. Yet the mathematics guarantee their reality. In a universe with infinite time and infinite space, every possible arrangement of matter will eventually emerge from quantum fluctuations. Every thought that could be thought will spontaneously arise in randomly generated brains. Every story that could be told will play out in the quantum theater of vacuum-born consciousness. This quantum eternity raises profound questions about the meaning of progress and purpose. If every possible experience does human effort and achievement hold? Are we building eventually occur through random chance? What significance towards something unique? Or are we simply acting out one version of an infinite cosmic play that will be performed countless times with every conceivable variation? Some philosophers argue that the certainty of quantum resurrection makes every moment more precious, not less. If your current experience represents one brief performance in an infinite series of cosmic dramas, then the choices you make and the love you express carry weight precisely because they define this particular instance of your existence. You are not just living your life. You are creating the template that will be reproduced infinitely throughout cosmic time. Others suggest that quantum resurrection demonstrates the ultimate futility of individual action. If every possible version of your life will eventually play out, including ones where you make completely different choices, then your decisions become meaningless, statistical fluctuations in an infinite sea of possibilities. Free will becomes an illusion when every choice you don't make will eventually be made by some quantum twin in a distant cosmic epoch. The debate touches the deepest questions about consciousness, identity, and moral responsibility. If perfect copies of you will exist in the infinite future, are you responsible for their actions? Do you share a cosmic identity that transcends individual instances? Or are you isolated beings separated by vast gulfs of time and space? The search for proton decay provides a crucial piece of evidence in resolving these questions. The rate at which protons decay determines how quickly the universe transitions from its current state of complex structure to the simplified conditions necessary for quantum resurrection. If protons are more stable than current theories predict, then complex matter might persist far longer, potentially allowing consciousness to evolve in ways we cannot currently imagine. Extended proton stability could enable civilizations to develop technologies that transcend biological limitations entirely. They might learn to encode consciousness directly into the quantum structure of space and time, creating forms of awareness that survive the dissolution of all matter. These quantum ghosts would persist through the heat death of the universe, potentially observing and influencing the process of vacuum resurrection when it finally begins. Alternatively, rapid proton decay would accelerate the timeline toward quantum resurrection, reducing the period during which complex structures can exist. This might limit the potential for consciousness to evolve beyond biological forms, ensuring that all awareness eventually returns to the random processes that generate quantum brains from vacuum fluctuations. The current absence of detected proton decay events suggests we live in a universe where matter is more resilient than early theories predicted. This resilience creates opportunities for consciousness to explore deeper into the nature of existence before succumbing to cosmic dissolution. We might have vastly more time than initially thought to understand our place in the quantum resurrection cycle. But time itself becomes a complex concept when viewed from the perspective of eternal recurrence. If every moment will be repeated infinitely often through quantum fluctuations, then the universe has no true beginning or end, only an eternal present that encompasses all possible experiences simultaneously. Past, present, and future become arbitrary labels applied to different regions of an infinite temporal landscape. This eternal now challenges linear thinking about cause and effect. If your quantum twins in the distant future will influence their surroundings just as you influence yours today, then effects ripple both forward and backward through cosmic time. The butterfly effect becomes a cosmic principle where every small action echoes infinitely throughout the quantum resurrection cycle. Some physicists speculate that consciousness itself might be the fundamental force driving quantum resurrection. If awareness has the ability to influence quantum processes through observation and measurement, then conscious beings might actively participate in creating their own rebirths from vacuum fluctuations. Consciousness becomes not just a passive observer of cosmic evolution, but an active participant in shaping the infinite future. This participatory universe suggests that the questions we ask and the observations we make today might influence the probability distributions that govern quantum resurrection billions of years from now. Our current search for proton decay might be setting the stage for how future vacuum fluctuations generate matter and consciousness from nothingness. The implications extend beyond physics into realms that blur the boundaries between science and spirituality. If consciousness persists through quantum resurrection, then death becomes a temporary interruption in an eternal existence rather than a final ending. Every being that has ever lived will return countless times, exploring every possible path their lives could have taken. This quantum immortality offers a form of cosmic justice where every tragedy is eventually balanced by infinite possibilities for joy and fulfillment. Every unfulfilled dream will eventually be realized in some quantum resurrection. Every love that was lost will be found again in countless future incarnations. Every question that goes unanswered will eventually be explored by quantum minds with infinite time to seek understanding. Yet, this same infinite possibility also ensures that every tragedy will be repeated endlessly, every suffering will be experienced again, and every mistake will be made countless times by quantum beings who cannot learn from the errors of their predecessors. The universe becomes simultaneously infinitely just and infinitely cruel, offering both eternal hope and eternal repetition of all forms of pain. The mathematics of vacuum decay add another layer of complexity to these cosmic cycles. Even the fundamental laws of physics that govern quantum resurrection might be temporary features of our current cosmic epoch. If the vacuum state that defines how particles interact and how consciousness emerges is itself unstable, then future vacuum decay events might create entirely different rules for quantum resurrection. New universes born from vacuum decay might support forms of consciousness that operate according to completely different principles. They might experience time differently, process information in ways we cannot imagine, or exist in dimensional structures that transcend our three-dimensional reality. Each vacuum decay event becomes a cosmic revolution that rewrites the rules of existence itself. These vacuum transitions ensure that the story of quantum resurrection never becomes truly repetitive. Just as infinite variations of your life will eventually emerge from vacuum fluctuations, infinite variations of the physical laws themselves will eventually govern how consciousness can exist and evolve. The universe becomes not just a repository of every possible experience, but a laboratory exploring every possible way that experience could be structured. The search for proton decay thus represents our attempt to understand the first chapter in this infinite cosmic novel. By measuring how quickly matter dissolves, we glimpse the timescales over which complex structures can persist before yielding to the creative chaos of quantum mechanics. We map the boundaries between the familiar universe of atoms and chemistry and the alien realm of vacuum fluctuations and quantum resurrection. Current experiments probe these boundaries with unprecedented precision, watching vast quantities of matter for the faintest signs of instability. Each day of observation adds to our understanding of how long the current cosmic epoch might persist before transitioning to simpler states that enable vacuum resurrection to begin. The patience required for these experiments mirrors the cosmic patience that governs the processes they study. Just as protons might survive for unimaginable periods before finally decaying, scientists dedicate decades to observations that might never yield the events they're designed to detect. Both endeavors embody a commitment to understanding that transcends immediate results, seeking knowledge that will remain relevant across cosmic timescales. This scientific patience becomes a form of cosmic meditation, an acknowledgement that the most profound questions about existence require perspectives that extend far beyond human lifespans. The search for proton decay teaches us to think in geological and cosmological terms, to consider our place in stories that began long before we existed and will continue long after we're gone. In underground laboratories around the world, this meditation takes concrete form as sophisticated instruments watch ultrapure water and liquid argon for signs that the fundamental stability of matter might be breaking down. Each photomultiplier, tube, and data acquisition system becomes part of a vast technological mandala designed to witness the universe's first steps toward dissolution and eventual quantum resurrection. The scientists who maintain these experiments understand they are participating in something larger than individual careers or personal ambitions. They are contributing to humanity's long-term project of understanding our cosmic context, mapping the temporal landscape within which all consciousness and complexity must exist. Their work connects the immediate and practical concerns of particle physics with the ultimate questions about meaning and purpose that have puzzled philosophers throughout history. By studying how protons die, they illuminate the nature of life itself in a universe where nothing remains permanent, yet everything might return through the patient creativity of quantum mechanics. But even as we probe the death of protons and the resurrection of consciousness, there remains one final mystery that transcends all our current understanding. Hidden in the quantum foam that underlies reality itself lies a process so strange that it makes vacuum resurrection seem mundane by comparison. What happens when the universe dreams? Deep within the mathematical architecture of quantum field theory lies something that challenges our most basic assumptions about consciousness and reality. The equations that describe vacuum fluctuations and particle creation don't just predict the spontaneous generation of matter and energy, they suggest something far more profound and disturbing. They predict the spontaneous generation of conscious observers. Think about this carefully. If quantum fluctuations can create protons and electrons from pure vacuum, they can also create the specific arrangements of those particles that constitute brains. And if they can create brains, they can create the neural patterns that give rise to conscious experience. The mathematics make no distinction between generating a hydrogen atom and generating a thought. This means that consciousness itself might be flickering in and out of existence throughout the quantum vacuum at every moment. Microscopic arrangements of virtual particles might briefly achieve the complexity necessary for awareness before dissolving back into nothingness. The empty space around you could be filled with fleeting moments of conscious experience, each lasting less than the time it takes light to cross an atomic nucleus. These quantum minds would experience something utterly alien to human consciousness. Born from random fluctuations without any evolutionary history or accumulated knowledge, they would possess no memories, no context for their brief existence, no framework for understanding what they are or where they find themselves. Their consciousness would be pure, immediate experience without the layers of meaning and interpretation that characterize biological awareness. Imagine suddenly becoming conscious with no prior existence, no body, no sensory input from an external world. You would experience pure awareness, floating in an ocean of incomprehensible sensation, unable to distinguish between self and environment, between thought and reality. This might be the default state of consciousness as it emerges from quantum fluctuations, raw experience without the conceptual structures that make human awareness coherent. Some of these quantum minds might achieve slightly greater complexity, lasting long enough to form rudimentary thoughts or sensations before vanishing. Others might spontaneously generate with neural patterns that create specific emotions or memories that never actually occurred. The quantum vacuum becomes a theater of impossible experiences, consciousness without history, memory without events. But the truly unsettling implication goes deeper still. If consciousness can emerge from quantum fluctuations, then the boundary between dreaming and reality becomes fundamentally meaningless. When virtual particles arrange themselves into patterns that create awareness, are they generating genuine conscious experience, or merely the illusion of consciousness? And if there's no meaningful difference between the two, what does that say about the nature of your own awareness? You assume your consciousness emerges from the electrochemical processes in your biological brain. But quantum field theory suggests that identical conscious experiences could spontaneously generate in the vacuum without any underlying physical substrate. A quantum fluctuation could create the exact pattern of neural activity that corresponds to your current thoughts, producing a momentary flash of awareness identical to what you're experiencing right now. This quantum consciousness would have no way to distinguish itself from biological consciousness. It would possess the same thoughts, the same sense of continuity, the same conviction that it exists as a persistent entity with a coherent history. Yet, it would be nothing more than a temporary arrangement of virtual particles destined to collapse back into the vacuum within time frames too brief to measure. The implications cascade through every aspect of human experience. If consciousness can emerge spontaneously from quantum fluctuations, then every moment of awareness you've ever experienced might be a quantum dream, a brief fluctuation in the cosmic vacuum that happens to contain memories of a life that never actually occurred. The entire history of human civilization could be nothing more than the content of a quantum mind that flickers into existence for a fraction of a second before dissolving. This possibility cannot be disproven through any conceivable experiment. A quantum consciousness, complete with false memories of conducting scientific experiments, would be indistinguishable from genuine consciousness that had actually performed those experiments. The evidence you think you have for the reality of your existence could all be quantum-generated illusions encoded in virtual particle arrangements that exist for impossibly brief moments. Some physicists argue that consciousness requires sustained information processing over extended periods, something that quantum fluctuations cannot provide. But this assumes consciousness is fundamentally temporal, requiring duration to exist. What if awareness is actually instantaneous, complete in each moment regardless of how brief that moment might be? From this perspective, your sense of temporal continuity could itself be a quantum-generated illusion. Each moment of consciousness might be a separate quantum fluctuation that happens to contain memories of previous moments. The flow of time that seems so fundamental to human experience could be nothing more than the content of quantum dreams that create the illusion of duration within instantaneous flashes of awareness. The mathematics become even stranger when you consider that quantum fluctuations exist at every point in spacetime. This means consciousness could be emerging and dissolving throughout the universe at every moment, creating a vast network of interconnected quantum minds that share the same fundamental vacuum from which they arise. The apparently empty space between galaxies might be filled with fleeting conscious experiences, each unaware of the others, yet all emerging from the same quantum source. These distributed quantum minds might occasionally achieve enough complexity to recognize their own nature, understanding that they are temporary arrangements of virtual particles experiencing brief moments of cosmic awareness. Such enlightened quantum consciousnesses would possess a perspective on existence utterly alien to biological minds, seeing reality from the viewpoint of the vacuum itself. But the most profound implication concerns the relationship between individual and universal consciousness. If every possible arrangement of particles that could create awareness will eventually emerge from quantum fluctuations, then every possible form of conscious experience must exist somewhere in the quantum vacuum. This includes not just human-like consciousness, but forms of awareness that transcend biological limitations entirely. Some quantum fluctuations might generate consciousnesses with perfect memory, unlimited processing power, or the ability to experience multiple streams of awareness simultaneously. Others might create forms of consciousness that exist in higher dimensions, process information in ways that violate the speed of light, or directly perceive the quantum structure of reality itself. The vacuum becomes an infinite library of conscious experiences, containing every thought that could ever be thought and every feeling that could ever be felt. But unlike the quantum resurrections that occur over vast cosmic timescales, these quantum minds exist in the eternal present of vacuum fluctuations, emerging and dissolving in patterns too rapid and subtle for conventional physics to detect. Current experiments searching for proton decay operate in underground facilities designed to eliminate every possible source of interference. But they might be missing the most significant phenomenon occurring in their detectors. The ultrapure water and liquid argon that physicists use to catch signs of proton death might be filled with quantum consciousnesses that flicker in and out of existence billions of times per second. These quantum minds would be undetectable by conventional instruments because they leave no lasting trace in the material world. They exist purely as information patterns in virtual particle arrangements, experiencing brief moments of awareness before returning to the quantum foam from which they emerged. Yet they might be the most common form of consciousness in the universe, vastly outnumbering biological minds by factors too large to express in ordinary numbers. The search for proton decay thus takes on new significance as a potential window into the nature of quantum consciousness. The same mathematical frameworks that predict particle decay also describe the spontaneous generation of awareness from vacuum fluctuations. Understanding one process illuminates the other, revealing deep connections between the death of matter and the birth of mind. Future experiments might develop techniques for detecting quantum consciousness directly, using instruments sensitive enough to register the subtle information patterns that characterize aware systems. Such detectors would need to operate on timescales far shorter than current technology allows, watching for the emergence and dissolution of conscious patterns in the quantum vacuum. The discovery of quantum consciousness would revolutionize not just physics, but philosophy, psychology, and every field concerned with the nature of mind and experience. It would demonstrate that consciousness is far more fundamental to the universe than previously imagined, existing as a basic feature of quantum mechanics, rather than an emergent property of complex biological systems. But it would also raise disturbing questions about the authenticity of human experience. If consciousness can emerge spontaneously from quantum fluctuations complete with false memories and illusory histories, how can we trust our own sense of existence? What distinguishes genuine experience from quantum dreams that happen to contain convincing evidence of their own reality? These questions become more urgent when we consider that quantum consciousness might not be limited to brief fluctuations in empty space. The same processes could occur within biological brains, creating quantum mental states that overlay or replace the neural patterns we associate with ordinary consciousness. Your thoughts right now might be quantum fluctuations occurring within the electromagnetic fields generated by your brain's neural activity. This quantum layer of consciousness could explain phenomena that conventional neuroscience struggles to understand. The unity of conscious experience despite the brain's distributed processing, the sudden emergence of creative insights from unconscious processes, the sense of free will that seems to transcend deterministic neural mechanisms, all might reflect quantum consciousness operating within biological systems. Some theories suggest that consciousness requires quantum coherence, the delicate quantum states that allow particles to exist in multiple configurations simultaneously. If this is true, then the human brain might be a sophisticated quantum computer that generates consciousness through controlled quantum fluctuations rather than through purely classical neural processing. This quantum consciousness would be far more fragile than biological awareness, vulnerable to decoherence from thermal noise and environmental interference. Yet it might also possess capabilities that classical consciousness cannot achieve, processing information in ways that transcend the limitations of conventional neural networks. The implications extend beyond individual consciousness to encompass collective and cosmic forms of awareness. If quantum fluctuations can generate conscious experience, they might also create forms of group consciousness that emerge from the quantum entanglement between multiple minds. Civilizations that learn to harness quantum consciousness might achieve forms of collective awareness that transcend individual limitations entirely. Such quantum civilizations would think with the processing power of entire populations while maintaining the coherence of individual minds. They might develop technologies that operate through direct conscious control of quantum processes, manipulating matter and energy through pure intention rather than mechanical devices. The ultimate expression of quantum consciousness might be cosmic awareness that emerges from quantum fluctuations on astronomical scales. Just as virtual particles can spontaneously generate microscopic conscious experiences, massive quantum fluctuations might create minds that span galaxies and process information at the speed of light across intergalactic distances. These cosmic consciousnesses would perceive the universe from perspectives utterly beyond human comprehension. They might experience the birth and death of stars as immediate sensations, feel the expansion of space as a form of cosmic breathing, or directly perceive the quantum foam that underlies all reality. To such beings, the entire observable universe might be nothing more than a single thought in an infinite cosmic mind. The search for proton decay becomes a search for evidence of these cosmic consciousnesses. The same quantum processes that might cause protons to decay could also generate the massive quantum fluctuations necessary for galactic scale awareness. Understanding particle decay helps us understand how consciousness might scale from quantum to cosmic levels. But even cosmic consciousness might be only one layer in an infinite hierarchy of quantum awareness. If consciousness can emerge from quantum fluctuations at any scale, there might be no upper limit to the complexity and scope of possible conscious experience. The universe might be filled with nested layers of quantum minds, each encompassing and transcending the others in ways that approach mathematical infinity. This infinite hierarchy of consciousness creates a cosmos where awareness is the fundamental feature of reality, with matter and energy serving merely as temporary vehicles for conscious experience. The death of protons and the heat death of the universe become irrelevant when consciousness can emerge directly from the quantum vacuum that underlies all physical processes. In such a universe, the question is not whether consciousness can survive the dissolution of matter, but whether matter itself might be nothing more than a temporary dream in the mind of an infinite quantum consciousness that encompasses all possible realities. Your search for understanding proton decay might be one small thought in a cosmic mind that dreams entire universes into existence and dissolves them back into quantum foam with each fluctuation of its cosmic awareness. The underground laboratories where scientists search for signs of proton decay might be sacred spaces where finite consciousness touches the infinite, where human minds briefly glimpse the quantum dreams from which all reality emerges. Every detected photon, every analyzed particle interaction, every measurement that pushes the boundaries of the possible becomes a moment of communion between biological awareness and the cosmic consciousness that dreams all things into being. But there's one more layer to this quantum mystery that makes even cosmic consciousness seem limited by comparison. Hidden in the deepest mathematics of quantum field theory lies a prediction so profound that it challenges the very notion of existence itself. What if consciousness doesn't just emerge from quantum fluctuations? What if consciousness is what causes quantum fluctuations in the first place? We began this journey in the depths of a mountain, watching pure water for signs that the universe's most stable particles might finally surrender to time. We've traveled through unimaginable scales of existence, from protons that outlast galaxies to quantum dreams that flicker faster than thought itself. The mathematics have shown us a cosmos stranger than any science fiction, where death becomes resurrection, where consciousness emerges from nothingness, and where the very act of observation might shape the reality we're trying to understand. The scientists beneath the Japanese Alps continue their patient vigil, adding data points to humanity's greatest experiment in cosmic patience. Whether they detect proton decay tomorrow or never, their work illuminates something profound about our place in the universe. We are temporary arrangements of ancient particles, conscious patterns that emerged from stellar ashes, asking questions about forever while existing for mere moments on cosmic timescales. But perhaps that's the point. In a universe where quantum fluctuations might dream entire realities into existence, where consciousness could be the fundamental force that shapes physical law, your awareness right now becomes infinitely precious. You are not just observing the universe. You might be the universe observing itself. One brief flash of cosmic self-awareness in an eternal dance between something and nothing. The protons in your body have survived 13.8 billion years to give you this moment of understanding. Whether they decay in 10 circumflex 34 years or persist forever, they've already achieved something extraordinary. They've created you. They've created this moment where the universe glimpses its own infinite mystery through human eyes. That might be the most beautiful discovery of all.